seems like finding the sources of magnetic fields would be a logical place to start, but we're actually going to start with forces on moving charges. So when we have a charged particle and it's moving through a magnetic field, I'm going to give this thing a charge of positive Q, and it's moving through a magnetic field. If this were an electric field, we would see movement in this direction. But it's not an electric field, it's a magnetic field. First I want to start with a formula, and then I want to try and explain this a little bit. My force is going to be equal to Q V cross B, and this is something called a cross product. It is a vector operation. You actually usually pick up the cross product as a mathematical thing in vector calc, like a calc 3 sort of thing, but we don't actually need all of this. So the point of a cross product is that it's going to give us both a magnitude and a direction. So it's a vector operation that gives us an answer that's a vector. What we are going to do instead is do the magnitude and the direction separately. So for the magnitude of this force is going to be Q times magnitude V, magnitude B, times the sine of the angle between V and B. That's how you'll see it written a lot of the time. The way that I would like to write this is Q, V, B perpendicular. What that means, right now, my speed, my velocity, and my B field are perpendicular. So if I have 100 meters per second, a Q of half a coulomb, and a B field of 4 Tesla, I would just get half a coulomb, 100 meters per second, 4 Tesla, half times 4 is 2, times 100 is 200. That's what I would do as far as finding the magnitude. If I had a velocity vector that were this way, and I get here maybe an angle of 30 degrees, then I need to break that velocity vector into 2 components. I'm going to have a component that is parallel to my field, call that V parallel, and a component that's perpendicular to my field. I'm going to call that V perpendicular. From my right triangle, if this is the angle I have, those are the same angle, V perpendicular is going to be equal to V times the sine of my angle. So if I still have 100 meters per second, then in this case I will have half a coulomb times 100 meters per second times the sine of 30 degrees times 4 Tesla. The sine of 30 degrees happens to be a half, so this works out to be 100 newtons. So I'm just taking the perpendicular portion and multiplying it. I need a little bit more because my magnetic force is a vector. So I need to figure out how I'm going to do this vector portion, the direction portion. To do that, I'm going to use something called a right-hand rule. There are plenty of variations of right-hand rule. And you can choose the one that works for you. I'm going to show you the one that I learned. I learned this because at the time that I was learning right-hand rule, my right hand was broken, so I couldn't actually move it. So the right-hand rule that I know, or that I'm the most comfortable with looks like this. If I've got the palm of my right hand, I'm going to hold my fingers in the direction of the magnetic field. Which isn't too bad to remember, because you pretty much always end up drawing multiple field lines, multiple fingers. That makes things easy. Fingers point in the direction of the magnetic field. Your thumb points in the direction of the velocity. And when you do that, then you will have the force shoots out of your hand, Iron Man style. That's really it. So if I have this situation back here, I've got a velocity that points to the right. Let me get rid of this one for a moment. I've got a velocity that points to the right, and I have a magnetic field that points upward. So if I lay my hand down, so that my right hand down, so that my thumb points to the right, and my fingers point up toward the top of the page, what I get is a force that comes out. And outward is the dot with the circle, or without the circle. You'll see it both ways. If I have a velocity that points into the screen, and I have a magnetic field that points in this direction, I'm going to point my thumb into the screen and rotate my hand until my fingers point up and to the right. When I do that, I get a force that points this way. My force will always be perpendicular to my velocity. I will always be perpendicular to my magnetic field. My velocity and field don't have to be perpendicular to each other, but my force, which comes from the vector operation of crossing V and B, my force will always be perpendicular to both of these. Any two lines establish some kind of a plane. So whether these intersect at 90-degree angles or not, they both live in a plane. My force vector, if these were V and B, in whichever order, my force vector would be into or out of this plane. It's going to have to be perpendicular to the plane that contains both of those. If I have a magnetic field that's this way, and I have a velocity that doesn't cross any field lines, then my force is 0. So I have to cross field lines to be able to have this magnetic force. If I do, then I figure out the magnitude by doing QV perpendicular times B, and I figure out the direction by doing right-hand rule.